Hello. Welcome to our evening with Dr. Jennifer Francis. We're glad to have you with us, and we think you're going to really enjoy this presentation. I'm Roberta Longley, and I am with the Eastham Climate Action Network, the group that's sponsoring tonight's webinar in partnership with the Eastham Public Library. This is a Zoom webinar, and that means that your camera and mic are off. So no worries that anyone can see or hear you. Also, the webinar is being recorded this evening. Before introducing Jennifer, I thought I'd share with you a bit about the Eastham Climate Action Network, also known as ECAN. ECAN is a group of volunteers working to inspire and mobilize Eastham's residents, businesses, and the town to work towards net zero greenhouse gas emissions in order to help reduce the impact of climate change. Just a year ago, our initial effort was to advocate on behalf of a town meeting article to establish as town policy the goal of eliminating net greenhouse gas emissions to net zero as soon as technologically and economically feasible. Happily, the article passed overwhelmingly at the Eastham's town meeting in September. ECAN continues to look for ways to advance efforts towards a net zero emissions future. And one way is to offer opportunities for people to learn more about climate change and what we as individuals and our communities can do to be a part of the solution. We want to encourage your interest and involvement with our work. My fellow ECAN member, Charlie Sullivan, will talk a bit more about those opportunities towards the end of tonight's program. Now, for this evening's presentation, we feel extremely fortunate to have Dr. Francis with us this evening to share her knowledge about the rapidly changing Arctic and the worldwide impact resulting from these changes. As you know, Jennifer Francis is a senior scientist at the Woodwell Climate Research Center in Falmouth, Massachusetts. Prior to joining the Woodwell Center, she spent 24 years as a research professor at Rutgers University in the Department of Marine and Coastal Sciences, where she studied Arctic climate systems and how rapid Arctic changes are affecting areas beyond the Arctic, particularly extreme weather in the Northern Hemisphere. In recent years, Jennifer has devoted part of her time to public communication in order to help non-scientists gain a deeper understanding of why the climate is changing and how these changes will continue to affect each and every one of us in profound ways. Dr. Francis plans to give a 45-minute presentation that'll be followed by a question and answer session. At any time this evening, feel free to include your question in the question and answer box at the bottom of your Zoom screen. I learned that Jennifer and her husband sailed around the globe during the 1980s, including the Arctic. And this was where I understand she got her first experience with the Arctic phenomenon. The two of them are still roaming, spending a good part of the year living on a sailboat, which is not a bad place to live or work. I think tonight, Jennifer happens to be in St. Thomas. Can you help me welcome Dr. Jennifer Francis?
Hello, everyone. Thank you so much, Roberta, for that very nice introduction. Thank you, everyone, for tuning in. And thank you for inviting me to be part of this event tonight. So let's just jump right in. I am going to share my screen. And get started. Okay. So the main topic I'm going to talk about tonight is why you should all care about the fact that we're losing most of the ice in the Arctic. It's melting very fast, it's warming very fast, and all of the reasons why it should matter to all of us, not just people up in the Arctic. One of those reasons is that the Arctic is actually affecting our weather patterns down here in the United States and all around the Northern Hemisphere. One such example of that, you'll remember just about 6 weeks ago, we had this incredibly severe infiltration of Arctic air that extended all the way down into Texas and even to the border with Mexico. It caused incredible disruption and distress to people living in that area. And of course, you know, it's February. We get these cold spells happening every year. That's not unusual. But what made this particular one so unusual, as you can see on this map, it covered a very large area of the United States. It lasted for a very long time. And that cold air penetrated so far south. And Dallas set a new record of -2 degrees Fahrenheit, which at the time was colder than parts of Alaska and Greenland. So what exactly caused this incredible extreme event, this cold winter attack? Well, just about every cold spell happens for the very same reason. It's because we see the jet stream, which is indicated here in this blue track here. That's also called the storm track or the jet stream, which you've seen on TV weather forecasts and so forth. That jet stream there is really the boundary between the Arctic air that usually sits farther north and the warm, more tropical air to the south. And when the jet stream takes one of these big southward dips like it did this past February, it allows the Arctic air to plunge way far south into places that aren't used to seeing that happen. But what made this particular one so extreme, as you can see this pink thing here sitting over the northern Midwestern states, called the polar vortex. And I know you've all heard of the polar vortex now. It really came into our dinner table conversation around 2014 when we had a very severe winter that year. But most people, I don't think, really know what the polar vortex is, and that term has been used incorrectly. So tonight you're going to learn what the polar vortex really is so that you can go tell everybody when they say it wrong. So what is this polar vortex? So if we're looking down here on the northern hemisphere, there's the United States and Europe and the Atlantic Ocean. Basically, we have these two features here. There's one that I already mentioned, this jet stream here in the light blue that encircles the northern hemisphere. It sits at about 5 to 9 miles above the surface. It isn't usually this straight at all. Usually it has these north-south wiggles in it, but we'll skip that part for now. But sitting on top of that is much higher up in the atmosphere, 10 to 30 miles above the surface, is what we call the stratospheric polar vortex. So it's much higher up in the atmosphere. It's only there in the winter. And it's these very strong west to east winds that keep this very, very cold air bottled up right over the North Pole. But every once in a while, what happens is this polar vortex splits up. It gets disrupted. And when that happens, we know that crazy weather is going to happen somewhere around the northern hemisphere. So sure enough, this year we had a major disruption of the polar vortex that started in late December and it continued all the way into early March. And it split up into these two separate circulations. One of them slid down over North America and the other one slid down over Siberia. And this took what was maybe normally just a regular old winter cold spell and really strengthened it and made it much worse because all this extremely cold air from way over the North Pole descended down over North America and made it that much worse. And you can see that when this happens, we also see the jet stream get all wavy like this. So that's what helped make that dip in the jet stream extend so far south because it had all this extra cold air reinforcing it from the stratospheric polar vortex. So that was over North America, but if we step back and look at the big picture, what was going on elsewhere at that same time? So here these blue colors are showing us where the air temperatures were much colder than normal over the central part of North America and over northern Eurasia, where that other part of the stratospheric polar vortex drifted down. But on either side of these very cold areas, we see just the opposite. And this is almost always what happens. When you get an extreme of one type occurring in one area, you tend to get the extreme of the other type occurring right next door. So you can see these red areas are where the temperatures are much, much warmer than normal. And I want you to notice, especially up in the Arctic here. So that cold air that has moved down over the continents came from the Arctic and left the Arctic much warmer than it would normally be. And this is what typically happens when we have these disruptions of the stratospheric polar vortex. So that's just one type of extreme weather event. And I should mention that there is some very recent research that suggests that these disruptions of the stratospheric polar vortex appear to be happening more often now. And we think that's actually tied to climate change, but that's a very hot research topic. But what we do know is that extreme weather events of a variety of sorts have been increasing. This graph is not produced by people like me studying these connections, but rather this is from an insurance company, Munich Re, you might have heard of. And of course, insurance companies really care about extreme weather because they end up having to pay the bills when they do a lot of damage. So they keep track of these things. So what you're looking at here in these different colors of bars going back to 1980 are different types of extreme events that have occurred over this time period. These red bars down at the bottom here are events that have nothing to do with weather. So there'd be things like earthquakes and volcanoes and tsunamis and things like that. Whereas these other bars are all related to weather in some way. And what you see is that just since 1980, we've seen a tripling of these extreme events related to weather. And just this past year in the United States, we broke the record for the most billion-dollar extreme weather events we've ever had, with 22 of them. So I'm going to step back even farther now and look at what the Earth's temperature has been doing over the last 20,000 plus years. So on the left side of this graph here is 20,000 years before, or BC actually. And this line here is showing you how the Earth's temperature has varied over that time period. So back here 20,000 years ago was the last time we had an ice age. It was when the Laurentide ice sheet extended all the way down to Massachusetts and created Cape Cod. And then we have later in this period, around 8,000 years ago, we have the most recent interglacial period, which is in between ice ages. And what you can see is that since that time, that blue curve is actually showing that the Earth was in a natural cooling phase. So all of these variations that I'm showing you here are due to natural causes. Humans had nothing to do with it up to that point. But of course, we all know that things are not normal anymore. They're not natural anymore. And instead of the Earth being in this cooling cycle, it's now warming abruptly. So there we are, where we are today, how the temperature of the Earth has changed. And if we look to the projections for the future, we're on this track to head towards something like 3 degrees Celsius of warming by the end of the century. So that's the temperature story. And this is another story that you don't hear as much about. And it's the fact that we are, by warming the oceans and warming the atmosphere because of the extra greenhouse gases that we've been literally dumping into our atmosphere since the Industrial Revolution, we've warmed the oceans and atmosphere such that now more moisture can be evaporated from the oceans up into the atmosphere. And so this animation is just showing you a snapshot for one day of what water vapor in the atmosphere looks like. This is actually from last September. And I picked this one because there's some features on here that are interesting to look at. There's Hurricane Teddy brushing by Bermuda. These are the remains of Hurricane Sally that just had gone into Louisiana. You can see some other swirls of moisture. So the tropics obviously are where most of the moisture in the atmosphere resides. You can see that very clearly with these red and orange yellow colors. But you can also see these really interesting tendrils that extend all the way up to the Arctic. And this is the result of storms that come across the higher latitudes and basically transport that moisture far poleward. So the moisture story is really interesting. And as I said, what we're seeing now is an increase in the amount of water vapor in the atmosphere because of this warming. And the reason this is so important is because that moisture in the atmosphere is literally the fuel for storms, for hurricanes, and for the kinds of storms that we tend to get around Massachusetts as well, nor'easters and storms all over the world. So this water vapor is literally the fuel for storms. Water vapor is also a greenhouse gas. And so by having more of it in the atmosphere, we're making the original problem worse. So we started with an atmosphere that had a certain amount of carbon dioxide in it. We've added a lot of carbon dioxide to it. That has created this increased evaporation. And so the original effect now has been made stronger because of this extra moisture in the atmosphere. So this is a type of a vicious cycle that there are many of these that occur in the climate system. And it's also called a positive feedback loop, which you also might have heard that term. So another effect of this water vapor is that, of course, there's more moisture available when a storm does come along, and we're seeing a very clear increase in the frequency of heavy precipitation events. And you'll see that in the Northeast of the United States is where we're seeing the biggest increase, 55% just since the 1950s in heavy precipitation events. So water vapor is a very big deal. Okay, so let's go back to temperature now and look at this past year, 2020, and how the temperatures around the world differed from what we consider to be normal. And of course, 2020 tied for the warmest year on record. This is such bad news. We've had 9 of the 10 warmest years in the last 10 years. So we're on a very clear path here, as I showed you in that graph going back 20,000 years. But what we see here is just for 2020, there's yellows and reds pretty much everywhere around the globe, showing that just about everywhere is warmer than normal. But you also notice the high Arctic here is where these reds are the strongest. And we are seeing the Arctic warming about 2 to 3 times faster than elsewhere overall. And especially in the summer, this is very clear. So we're looking at the temperatures of the Arctic in the summertime going back to the late 1940s. And you can see this very clear trend starting around 1990 or so. And this past summer, we set an all-time new record for the warmest temperatures in the Arctic that we've ever recorded. Along with these warm temperatures, of course, as I mentioned in the very beginning, is the fact that we're melting the ice in the Arctic. So this graphic produced by a cool guy he's now at Colorado State University, has put together this graphic that illustrates how the thickness of the sea ice floating on the Arctic Ocean has changed just in the last 40 years. And so you can see the years ticking by here. The bright white and yellow colors are where the ice is the thickest. And as this animation goes through time, you can see that as we get up to present day, those thick ice types are virtually gone. There is no more thick ice left in the Arctic Ocean. Alongside this, we can see what's been happening to the sea ice volume, which is the area covered by the ice multiplied by the thickness of that ice. And literally the volume of the ice in the Arctic has diminished by about 75% just in 40 years. It's just an amazingly huge change over a very short time period. And what does this mean for us? So I mentioned that the Arctic has a lot to do with pretty much everywhere on the planet. And another aspect of this is how the aerial coverage of the ice has changed. So here we are again looking down on the Arctic Ocean. There's Greenland and there's Alaska. And typically in the summer, we'd see the Arctic Ocean pretty filled up with ice, even at its lowest extent, which is generally in September. But if we jump here now to 2012, which was when we measured the lowest amount of sea ice ever recorded, you can see that the white ice here is much, much smaller. And this red yellow color here is where there used to be ice. And so much more of the Arctic Ocean now is, instead of being bright white ice, is now dark ocean. And that has a huge impact, because instead of reflecting most of the sun's energy that hits it, hits the Arctic Ocean, now much more of that sun's heat is being absorbed into the water. And this sets up another one of these vicious cycles. And in fact, the Arctic is full of these vicious cycles, or these feedback loops. So the Arctic is literally darker now. The surface is darker, and it's absorbing more heat from the sun. And this is key, because this sets up this feedback loop where we absorb more heat into the ocean, and that melts more ice, which exposes more open water and heats up even further. So another one of these vicious cycles. And just by losing this ice cover in the Arctic, and also the snow cover during the spring on land areas, those two factors together have made global warming somewhere between 25 and 40% stronger than it would have been if that vicious cycle weren't in place. By warming the Arctic so fast, because of all these different vicious cycles, we're also accelerating the melt of Greenland. And of course, this is a serious issue, because that ice that's sitting on land, when it melts, it flows into the ocean and actually adds mass to the ocean. And this is right now the single biggest factor contributing to sea level rise. And that, I know, is a big issue for people living in Eastham. And by warming the Arctic so fast, we're also thawing the permafrost, which is the frozen soils in the high Arctic land areas. This is also a big deal, because as that permafrost thaws, that soil contains a lot of organic matter. So old plants and animals that died, hundreds of and maybe even thousands of years ago, are now thawing out. And so the microbes in the soil are able to digest that organic matter. When they do that, they release carbon dioxide and methane into the atmosphere. And of course, those are both greenhouse gases, and it sets up another one of these vicious cycles or feedback loops by adding more greenhouse gases to the atmosphere. And the final one here is really where most of my research resides, and that is trying to understand how weather patterns are being affected by the rapidly warming Arctic. So that's what we're going to talk about for the most part from now on. And how does this happen exactly? Well, if you think about a layer of air that extends from Cape Cod all the way up to the Arctic, we know it's warmer generally in Cape Cod than it is up in the Arctic. And we also know that warm air takes up more room than cold air. And warm air expands. So this layer of air is actually taller or thicker over Cape Cod than it is up in the Arctic. And this creates a hill in the atmosphere. So if you were sitting on top of this layer of air looking towards the north, you would be looking down a hill. And the air sitting up there wants to flow down that hill, just like water wants to flow down the side of a mountain. And this creates a wind. Now, normally you'd think, oh, it's blowing from south to north, but no, it's because the Earth is spinning, everything that moves in the northern hemisphere gets turned to the right, and that includes moving air. So this sets up the west to east winds that we call the jet stream. Now, remember that the Arctic is warming much faster than areas to the south. And so what's happening to this layer is that it's getting thicker, faster over the Arctic than it is down over the United States. And this is making that hill in the atmosphere less steep. So there's less force driving that wind blowing down that hill and then getting turned to the right. And as a result, we're seeing the westerly winds of the jet stream weakening. And we know that when the jet stream is weaker, it tends to be deflected more easily from its west to east path by things like mountain ranges or even blobs of of ocean temperatures that are different from normal. And so the jet stream ends up taking this more meandering path as it travels around the northern hemisphere. And so why do we care about that? Well, it turns out these waves in the jet stream are what create our weather. So we already talked about the fact that the jet stream separates the cold Arctic air to the north from the warmer air towards the tropics south of the jet stream. So if if the jet stream is north of you, then you're in generally warmer than normal conditions. And if it's south of you, then it's typically colder than normal. But in addition to that, the wave itself creates motions in the atmosphere that generate the high and low pressure areas that you see on a TV weather map. So this part of the jet stream, where the winds are coming from the northwest, tends to create high pressure. The conditions tend to be dry, they tend to be blue skies. Whereas this part of the jet stream, where the winds are coming from the southwest, is where you tend to have stormy conditions. And so when we get our nor'easters along the East Coast, we are in this part of the wave of the jet stream. So that's a very nice, simple picture. And unfortunately, the real jet stream doesn't behave anywhere near as nice as that schematic I just showed you. These are real winds showing you what the real jet stream looks like. So these yellow and red colors are where the winds are the strongest. And you can see that it's pretty much of a god-awful mess of swirls and changing. But you can generally see how the winds blow around the northern hemisphere, generally from west to east, but with all these different swirls and waves happening. So there are times when the waves are small, when they move fast across the continent, and then there are times like this where they're large and they tend to get stuck in one place. And this is a key piece of the research that I'm working on, and a key part of the idea that I think is happening is that because we're warming the Arctic so fast, we're weakening those winds, we are tending to see these larger waves forming in the jet stream. And so our weather associated with those waves is becoming more persistent. It's like our weather tends to get stuck in one place more often. So just to kind of drive this point home a little more, what I'm showing you here are two examples of when on the left here from November 2013, when the Arctic was very cold. We're looking down on the North Pole here. You can see Greenland and North America. When the Arctic is very cold, the jet stream tends to be quite straight as it blows around the northern hemisphere. But when those pools of cold air move south, and we have one of these Arctic outbreaks of cold air, like the one that happened in February, then we tend to see the jet stream taking these much larger waves. And in this particular case, the West Coast was high and dry. We were seeing some stormy conditions along the East Coast. And of course, the center of the country was very cold. And if we look at what the real jet stream was doing at that time, again, you can see as we look down in the North Pole here, these, again, red and yellow colors are where the winds are strongest. There's North America. And you can see that the pattern is very similar to this case that happened back in 2014, where we also had a very severe cold outbreak. So I just to kind of head towards wrapping up here, I wanted to give you a little taste of the kind of research that I'm working on these days to try to understand the ways that the warming Arctic might be affecting our weather patterns. But, there's a lot of other changes and fluctuations that happen naturally in the climate system. And figuring out how these two things interact with each other is really interesting. One of the concepts or hypotheses that I have, I call it takes two to tango. And the way this works is if we look at a case here, just a schematic of the Pacific Ocean, there's North America. Back in the good old days when the Arctic was filled with nice thick sea ice, then when a wave in the jet stream came along, it really didn't have the Arctic didn't have much impact. It was pretty much the same one year to the next. And so there wasn't anything noticeable going on. But if we fast forward to what's happening today, and you can see this big chunk of ice that has melted away from north of Alaska here. And as I mentioned, by losing all that ice, we are now absorbing a lot more heat into the ocean where that ice used to be. So that happens during the summer when the sun is out, when it's warm. And then when the fall comes along and the cold air returns, we see that heat being released back into the atmosphere. So now let's think about a couple scenarios of what might happen with the jet stream. We could see a wave in the jet stream occurring in this location, but because that peak or ridge, that northward swing in the jet stream here is so far removed from that heat source, there really isn't much effect of that ice loss on that wave. But if the wave were to set up here, which looks a lot like what happened this past February with this big dip over the middle of the country, now this peak in the jet stream can tap into that heat and it makes the wave even larger, it makes it stronger, and it makes it more persistent. And so what also happens, which is I think a really interesting concept that they're also working on, is that when these waves get really big, they can send a lot of heat and moisture up into the Arctic, which is another one of these vicious cycles. So by transporting all this extra heat and moisture into the Arctic, we're making this ice melt even worse. Or in the fall, in the case of the fall, it would mean that the ice would freeze much slower. So that's the idea behind that research. And now let's focus in on Eastham, Massachusetts. And what are the main concerns related to climate change for you all and this part of the world? Well, I mentioned briefly sea level rise and the fact that it's actually accelerating. And I'm sure you've all seen evidence of this along your coast with erosion when a big storm comes along. It's, storms erode anyway, but it's just happening in a much bigger way. We're seeing more storm flooding because when we do get a storm, those waves and that storm surge are both riding on a higher ocean level now. And so the flooding extends farther inland. And that's, of course, affecting coastal properties and coastal infrastructure more. It's degrading our salt marshes. Rising ocean temperatures are another big impact on New England in general. It's having a big effect on fisheries. We know that, the lobster fishery is basically over in Long Island Sound and most of Buzzards Bay. It's doing pretty well up north still, but it's a big shift in that particular fishery. We're seeing different species moving into the region. We're seeing more toxic algae blooms that are related to temperature. And that extra heat out in the ocean can actually fuel stronger storms. That's going back to that water vapor story that I mentioned, so that when we have warmer ocean temperatures out there, there's more evaporation, and that is fueling stronger storms. Again, we're seeing these increased frequency of heavy precipitation events. This is leading to more frequent flooding of streams and rivers, and also heavy snows even. It depends, of course, on where that snow rain line, and typically Cape Cod is usually in the rain side of things, but we are seeing a tendency for some of the real blockbuster snowstorms in New England to be happening in the more recent years rather than the past. And that's partly because there's now more moisture for those storms to work with. We're also seeing more intense summer droughts. Last year was a great example. I was just reading an article the other day about how the Ipswich River basically dried up last summer for, I think, the very first time. And of course, this has big implications for agriculture, for our fresh water supplies, for drinking water, and for all the things we need fresh water for. And then, of course, that's also leading to an increase in wildfires. And then there's tropical storms. So this is a whole nother area of really interesting climate change research, trying to understand how tropical storms are going to change in the future. But as they affect Cape Cod, some of the implications are that the tracks are now able to continue farther north because that ocean temperatures are warm enough to support tropical storm characteristics. And for the same reason, the hurricane season is getting longer. We're seeing more tropical storms forming in May. In fact, they're talking about even starting hurricane season May 15th. And it's also extending longer into the fall. So remember, Hurricane Sandy was on Halloween, and so was Florence just a couple years ago, was late October. So this is a very disturbing trend that we're seeing, as well as a tendency for more erratic paths that the storms are taking. Of course, Sandy being the poster child for that. And there's evidence now that the movement of tropical storms is actually slowing down, which I think may be connected to the Arctic and the changes in the jet stream that we're seeing. So if you're not already depressed enough, this is the projection for basically how our region is going to change in terms of our summer climate by the end of the century. The end of the century sounds like a faraway time, but it's really, you know, some of our grandkids, I don't have grandkids yet, but maybe some of you do, will be around for the end of the century. So by then, if we stay on the track we're on right now, the climate of southern New England is going to be more similar to that of Deerfield Beach, Florida right now. So that's kind of a real visual, I think, to help people understand just how much the climate system is going to change. And so let's end by taking a look at the future. And I'm going to tell this story by going back to Arctic sea ice. But I could show you very similar graphs that look like the loss of Greenland ice sheet, the loss of ice on the Greenland ice sheet, or the degradation of permafrost. They all look very similar. But I'm going to talk about the sea ice story. So what you're seeing here is these are a combination of observations of the real sea ice. So this black line is actually what's happened to the area extent of summer sea ice as we can measure from satellites. And this gray area here and the other colors as well are simulations from these very sophisticated numerical computer models that we use to try to simulate how the climate system works. And as you can see, going back in time, the climate models have done a really amazing job of capturing how the sea ice has changed up until present day, which is what this yellow line is. To the right of this yellow line is our future. And what you see are there four different paths that we could potentially take. These are four different scenarios for the future. The red line here is the do nothing future. This is if we continue to burn fossil fuels as we have been, basically do very little to try to restrain our emissions of carbon dioxide and other greenhouse gases. But this green line here is if we can get our acts together. This is what we could hope for. It's a stretch, to be honest. This is not going to be easy, but it is possible. And if we all do our parts at all levels of all the way from personal to international, we could definitely keep the sea ice from not melting away. And that's what happens on this red curve, is that we would lose all of the sea ice in the Arctic by around 2050. That's what this is saying. But if we can stay on this green curve, then that's really, you know, what we can hope for. By keeping enough sea ice in the Arctic, we'll avert a lot of the extreme weather events that I've been talking about, as well as a whole lot of other adverse changes in the climate system. So all of our efforts should be focused on keeping us on this green line. So what kinds of things can we do then? Well, as I said, we have a lot of levers to pull. We have a lot of power. Out here on Cape Cod, we have a lot of people who really care about this problem because it's slapping us in the face. A lot of the impacts of climate change are happening right now, and we can see it very clearly. So some of the things that we could do to try to keep us on that green curve I showed you, there's a lot of personal choices we can make in terms of, you know, what kind of transportation, what kind of car we choose to drive, how much we drive it, how often we fly, what kinds of efficiencies we put in our homes, our insulation, our windows, what kinds of appliances we purchase. and thinking about every step of every day that we go through. How can we use less energy, less electricity? Because to get that energy to your home takes a lot of energy. And so by saving, say, an electron of electricity, you're actually saving way more than one electron. Then we can move up to the community government. And that's what this group is all about that invited me to be here tonight. And that is, first of all, in identifying and addressing the structures and property in your community that are vulnerable. And there are a lot, because it is a pretty low-lying area. We need to start planning proactively rather than looking back in time, because the weather that we used to have and the the behavior of the climate system that we're used to is not a good lesson plan for the future. We know that things are changing, and we know that we can do better if we look forward. We can support all our efforts to get away from fossil fuels and, of course, move towards renewable energy and towards conservation. And I encourage everybody to join committees like the one that's hosting this evening, and to even run for office, run for the planning board, run for an energy management committee, and get involved, because one person can make a huge difference. And I can tell you that from personal experience in my own little hometown in Massachusetts. And then, of course, it gets up to the state and national government. We need to vote for leaders who get it, who are not sticking their heads in the sand. One of the first things that I think should happen would be to stop subsidizing anything to do with fossil fuel, whether it's the creation of the fossil fuel or the infrastructure that supports it. And we need to instead spend that money on more incentives for renewables. We've made a lot of progress in a short time, just showing us how much we can change quickly in the right direction. And another thing that would help us get toward that goal would be to price carbon emissions appropriately, and not just the fossil fuel companies, but we all use those fossil fuels. So we should all be paying the appropriate price. We've been dumping greenhouse gases into the atmosphere, you basically using the environment as a dumpster for a long time without really paying the price for the degradation that's happened. And finally, thank you for being here tonight, because you are helping to educate yourself by listening to presentations by people who are truly studying this problem, who are real scientists, and then go and talk to people about it, because that's how the word is getting around. And I really do think the tide is starting to turn, and more people are recognizing that this is a problem that we definitely need to address. So I'm sorry to end this on another kind of sad note, but I'm showing you this painting done by the son of one of my graduate students, and he sent it to me, and it really just was very upsetting, because I see that this is the way he looks at his future. But I think that we can do a lot to keep us on that green line I showed you, and make this vision of his future be much different from the one that he's painted here. So with that, I want to thank you very much, and I look forward to answering some of your questions.
Thank you, Jennifer.
You're welcome.
The presentation was fabulous. You really made complex things simple enough for people like us to understand, and that really
Well,
changed.
thank you very much.
Yes, and your slides are fabulous.
I'm glad you could see him. I'm glad my internet was okay, because that's not always the case.
As you know, we have some time for questions that you've been putting in the Q&A box. We have Janice Riley from the Eastham Library with us this evening, who's been reviewing those questions, and she is going to direct them to Jennifer. So can we welcome Janice?
Thank you very much. Okay, we've got one question here, and we welcome many more because we only have one. I have a whole sheet of them of my own, but I won't monopolize our time. So Anne Welrich is asking, will the rise in sea levels affect the drinking water in coastal communities?
Yes, it could very well. Many areas, especially on Cape Cod, where the soils are so sandy and porous, as the ocean levels rise, that salt water can infiltrate into, the groundwater, the fresh groundwater. It really depends on the structure of the soils where you are, but this is a real problem. It's already being observed, especially in marsh areas where sometimes you drive along and there's just lots and lots of dead trees, and that's because that salt water has intruded to where those trees used to be growing in fresh water. So we're definitely starting to see that happen.
I will jump in with one of my own while we're waiting for the next one to come through. You've probably read the book. I haven't read it yet, but it looks really interesting. Under a White Sky, Elizabeth Colbert. She wrote The Sixth Extinction. And this is her new book. And among the many interesting things that I read about in a review was that the title comes from this idea of geoengineering as a way of writing climate change. And this particular one is something about putting particles into the atmosphere that would deflect light that was heating up the CO2, but the sacrifice was the sky would become white instead of blue. So I'm wondering, do you think that this is a good idea to kind of engage in this new technology rather than actually do some of the things that you've been talking about?
So there's a lot of aspects to geoengineering. One of them, like you described, where we put these particles up high in the atmosphere where they would reflect sunlight, and so that sunlight would never make it to the earth, and so it would have a cooling effect. And we know this works because when there's a major volcanic eruption, it basically does that. It puts all these particles up in the atmosphere, and the really big volcanic eruptions have actually cooled the earth by a couple of degrees for a year or two. So we know this works. Other types of geoengineering are extracting carbon dioxide from the atmosphere using various types of technology. The best way to do that, in my opinion, is through natural means, which is trees are very good at extracting carbon dioxide from the atmosphere. And there's a lot of other good reasons to have a lot of trees around. But generally, the types of geoengineering where we're manipulating the atmosphere even further, and we've already done so much damage to the climate system, to think about actually injecting another substance artificially into the atmosphere. There's a couple of real big problems with that. First of all, we don't really know how things like droughts and storms will respond to a huge change in the way the energy is distributed around the earth that would result from putting those particles in the atmosphere. And you could think about how if one country decided they were going to do that and another country ended up having a complete failure of their agricultural season for a year or two, then that's just going to create all kinds of international strife. The other problem with it is that it is going to cost a lot of money, and I believe that using those large resources that might go towards a geoengineering project would be much better spent doing the kinds of things that we know can reduce our emissions in the first place, supporting renewable energy, for example, not cutting down forests as much, especially the tropical rainforest. So I am a pretty staunch opponent of those kinds of geoengineering, although I am a big supporter of trying to figure out how to extract carbon from the atmosphere if we can at scale, which is a big ask.
Wonderful, wonderful answer. Thank you. I was feeling a little about the same way, but I'm certainly not studied in it. So we have some questions coming in now. This is one that says, how can we best engage our Fox News friends and relatives who have a very different accepted narrative? Possible or forget it? Thank you.
Well, I think there are people out there who they just aren't going to listen no matter what you say. And I don't think it's worth wasting our breath on them. I think there's fewer and fewer of them as we go through time, because Mother Nature is doing our job for us. She's demonstrating, like with the fires out in the Western states, for example, that are so clearly tied to heat waves and the drought that's been ongoing out there basically for several years. Those are very clearly connected to climate change. Sea level rise is very measurable. You know, there's no other explanation for why the seas would be rising other than the heat that we've been putting into the atmosphere. I often win people over by showing them what's happening in the Arctic, because, you know, like I said, we've lost 75% of the Arctic sea ice in only 40 years. And the Earth used to be on a cooling path before we started putting greenhouse gases into the atmosphere. There's really no other explanation. And you can challenge people, you know, you show them, you talk about, well, you know, this is happening in your backyard. How do you explain it? And so, you know, but I wouldn't waste my breath on the people who are just, you know, have their heads really stuck down in the sand and don't want to listen.
We have a question. This is from someone in the library, but I don't know who. What are some of the less obvious heavy uses of petroleum that we could reduce using? I'm thinking about plastics, but are there others? Oh yeah, I guess this is from Deb. So are there others that we can reduce besides petroleum?
Well, you know, it's tough because petroleum, we've built our economy on petroleum, basically on fossil fuels. Some of them are easier to change than others, and that's why electrifying as much as we can is a great way to get off of petroleum, because anything that we can use electricity for, we can create that electricity in other ways. We can use wind, we can use solar, we can use a variety of different things. Where it's harder to transition is things like, you know, flights, airplanes. They're talking about creating electric airplanes. I think they're going to start flying some on short distances soon, but that is one of the harder ones to eliminate. Cement and concrete also use a lot of petroleum, a lot of energy. Aluminum is another one. Takes a lot of energy. So recycling those aluminum cans, if you don't recycle anything else, recycle your aluminum cans, because it takes just an amazing amount of energy to create one of those aluminum cans, and all aluminum for that matter. Those are the things that come to mind right now. We're moving pretty quickly now in terms of automobiles. I think we're going to see a big shift in automobiles towards electric vehicles. That seems to be underway, and people are not upset about that, because electric cars are great. They're so much cheaper to run. They're really fun to drive. They are quiet. So, you know, there's a lot of upside to some of the changes that are going to happen.
Nancy Higgins is asking, is it possible that the sea ice would be restored with the use of renewable energy practices?
It's physically possible. So that green line that I showed on that future graph there is probably the best we can hope for, would be to halt the melting of the ice. It would be tough to get it to grow back, because we've already put so much heat into the oceans. And you know, all the heat that's trapped by the greenhouse gases, 95% of it goes into the ocean, and it has already absorbed a whole lot of that heat. And it's going to take many centuries for it to leave the ocean. And you know, there's the whole current system in the Atlantic, for example, and there's a branch of the Gulf Stream that extends all the way up to the to the Arctic Ocean, and that is already starting to melt the ice from underneath. We're seeing what researchers have called the Atlantification of the Arctic. So it's because all this warm Atlantic water is now penetrating up into the Arctic Ocean, and so having that up there, which is a very slow process in the climate system, is going to make it tough to restore the ice. So I think the best we can hope for is that green line, which basically keeps it at some level that's lower than today, but not nothing.
And here's a very practical question. What change in appliances can we use? I think to keep our carbon footprint to a minimum.
Yeah, so if we include HVAC with that, I would suggest that anytime anybody switches out their heating system or their cooling system would be to switch to a heat pump type system. And there's a lot of reasons to do that. For one thing, they're much cheaper to run, they're electric, but also Massachusetts has huge incentives if you do that. So it's just a much cleaner, a much more efficient way to heat and cool your house. Other appliances would be, if you've got some old air conditioners in your windows, or just old style air conditioners, they should be replaced because they are huge users of electricity, especially in the summer, obviously. And the newer ones are much more efficient than the old ones. Other than that, just updating your kitchen appliances with Energy Star certified ones. They are definitely much more energy efficient. And, it's not just for the good of the world, but it's also for your pocketbook. You're going to save a lot of money if you have more efficient appliances, and you'll get paid back over time.
Doesn't look like we have anything else. We have somebody who's saying, thank you so much for your time and inspiration.
You're welcome. I'm glad you were here.
I think that's it.
All right. Couple minutes to spare.
Okay, well, I guess I'm going to have to throw things over to Charlie. There's nothing else coming in. So Charlie Sullivan is going to wrap up, and I'm going to mute myself. Thank you very much.
Thank you, Janice. I am Charlie Sullivan, and I'm part of the Eastham Climate Action Network. Roberta's explained the mission of our group. We started in March 2020, and we really wanted to promote green energy alternatives in the town, and ultimately help reduce carbon emission from both town use, but also personal use and business use. So Jennifer, I got to thank you for that presentation. It was really interesting and thought-provoking. Your talent and expertise and giving of your time is so appreciative. And I also want to thank the Eastham Library, Deborah and Janice. Without you and your staff, we couldn't have done this. Your technical assistance, your marketing abilities, and your encouragement were all very much appreciated. And finally, I want to thank the participants tonight. Obviously, you're concerned like we are, and frankly, probably frightened about what kind of a world we're going to leave our children and grandchildren if we don't get carbon emissions under control. I think you've all seen the slogan or seen it on a bumper sticker, think globally, act locally. Well, Jennifer certainly got us thinking globally. And I think now we and each town and community have to act locally. State and federal funding and policies are important, but we're never going to be successful with reducing carbon emissions unless we have committed, dedicated volunteers in each community. And the Eastham can is part of that. So what I'm asking tonight is that if you live in Eastham, or if you live in any town on the Cape, join your local climate action network. There's one in all 15 communities. And we particularly want to get Eastham people to join with us. We need people from all backgrounds, all interests, and all talents. Everyone is welcome. Please join us. You can contact us on the email that you've seen on the screen, easthamclimateaction @gmail.com. Please be a part of the solution. And thank you so much for participating tonight. Good evening.